So, for people joining us here, um, we are talking about a rather ambitious project and effort to implement multi-computation in Wolfram language. And a way to think about what's going on here is this is kind of a fundamental rethinking of the evaluation process. So, in our usual evaluation process, so I mean, standard evaluation, it has two features. One, it recurses it recurses through expressions in, let's say, in a depth first order. I believe that's correct. And two, it reevaluates results in a depth first order. Do people agree with those statements? Unless the only reason it doesn't do this one, except for hold all functions, for hold functions. Does that make sense to people?
Yeah. What do you mean by re-evaluates?
If I say F and it evaluates to G, and G evaluates to H, it does all of that.
Sense.
So this is essentially, quote, spatial, space-like. This is essentially time-like. Okay? We do not have...
And I think that hold all can be described as arbitrary traversal order because there's nothing decided for hold all functions.
No, it's not. It's outermost. This one is leftmost, innermost, and that one is leftmost, outermost. Hold is outermost because what it's doing is it's gulping the arguments first. It's going function. It might be different from that. It might have its own control.
I think the point is that you can use that to simulate any evaluation order.
That's what I was going. Yes. That's what I was saying. It's like any traversal order you like. If we're talking about that,
right? And so now, oh gosh, did we not invite the people? Okay, so now we actually have this traversal order function, right? We have tree traversal order coming in version 13, right? Which is, at least for trees, a specification of this. But notice this is pure recursion ordering. This is not, do you understand what I'm saying? It's not reevaluation ordering. Does that make sense to people? No, yeah. Yes. Roger, Christopher, others, Carlo. I mean, does it make sense? Does Carlo know about this stuff yet?
The tree I saw this stuff. There's one thing I'm a little bit confused about. Maybe you could convince me. Like all this tree traversal stuff, like substitution order, etc. Isn't that like a detail that is largely orthogonal to like the whole ruler part of this? Does it really matter? Or can we just think about this as transformation of some kind of global state? And then
it matters a lot. This is part of the story of defining foliations, which is what we're about to come to.
No,
so far this doesn't matter. What's that?
No, I'm not saying it doesn't matter. I'm saying isn't that like completely separated from the whole evaluation graph? Like the details of whether it's
they're not. They're no more disconnected than space and time are disconnected. I mean, okay, so let's just play what what is the multi-computation idea? The multi-computation idea is also we have a branch-like separation. That is, we have, because in this one, what we're doing is, a key feature of this is we're always, the basic scheme is evaluate, quotes, depth first to reach a normal form. That's what our evaluation does, right? And it does that it does it recursing through the expression, recursing, reevaluating. Its goal is to reach a normal form. That makes sense? Whereas here, we also have branch-like separation, which are different possible orderings that these things can occur in, if that makes sense. Did that make any sense? Do I need to
Yeah, it
explain
does.
more?
But what does this look like if the underlying language is something that has a bunch of ifs, and you can take different branches of an if statement? Like,
I don't think it is an if story. I think you could say, okay, so you could write our pattern transformations in terms of ifs, right? Instead of doing pattern transformations, you could have a giant if bank, so to speak, okay? But what this is saying is, because we have pattern transformations, we have a natural way to generalize to the branch-like case. If we had a bunch of ifs, we wouldn't have a natural way to do it. Instead,
Ifs are deterministic.
I'm sorry?
Ifs are deterministic. That's a
Well, yeah, but I mean, I'm saying that there are, look, the point also is, okay, we had some examples last time. I don't know where they are. Like, for example, oh gosh, where are they? I had a nice example of a Fibonacci tree. Where the heck is it?
I mean, by the way, one thing with if is just, it's also just that, I mean, you can kind of just model if as a hold all function, can't you? I mean, like, there's nothing super special about it.
Yes. I don't think there's anything special about if. I mean, well, other than the fact that it's picking one branch.
Yeah. I think one thing that's special about if is that it needs a you need some element that has a non-standard evaluation order, I think, right? Otherwise, do you even get full computation capability if you don't? Think.
What do you mean?
Yeah, like at the core, you need to have if you didn't have if somewhere at the core, there you couldn't implement if maybe. Although maybe
Right.
with pattern matching,
it's not true.
You
with
could.
Pattern matching, you can absolutely implement if. Absolutely, you can. You know, combinators have no trouble implementing if. Let's see, maybe this has the Fibonacci case in it.
Or maybe it's a practicality then. I think that for a lot of languages, you need something that doesn't follow standard evaluation order.
Right, you do, but I mean, but once you have the hold all attribute, I think that makes it so anything you set the hold all attribute to can be that thing that doesn't follow standard evaluation order, if you know what I mean.
Yes, absolutely. Yeah.
Okay,
no,
so
if you have
this is-
hold all, you have it. I mean, it's like you have a lot more.
That's an example of Fibonacci done essentially multi-computationally. Okay, what that means is, in actual Fibonacci, you're adding things together. Here you are simply sort of, adding things as elements to a set, if that makes sense. Right? So what's interesting here is, in Fibonacci, we could do a search. Do you ever get to f of 2 or something, right? That's like a search type thing. Or we can do a different observation of this Fibonacci evaluation that is saying, just add up the total number of leaves. Does that make sense? Or we could do probabilistic, something which is like probabilistic programming, where we say, we try to address the question, we say all these different branches are different probabilities, and we simply say, what's the measure on the space of F1s, F2s at the end point, so to speak. Does that make sense to people?
One could, but why would one, so to speak?
Well,
I mean, if the goal is to get F7.
I know, but the whole point is, this is just an example of, a thing to realize is, okay, the thing we're trying to understand is, Okay, if you think about logic programming, okay, if this wasn't Fibonacci's, if this was, I'm sure I have another example here, if this was game configurations or something, right? You know, you're asking the question, does there exist one that has such and such a property? Can you derive it? Can you get from this game state to this other game state? And in that case, what you're asking is, does there exist a path here, as opposed to asking the question, what is the set of all possible game states? See what I'm saying?
Right.
What we're trying to understand is what multi-computation does is it gives you a richer version of evaluation. The evaluation that we have right now in terms of Fibonacci, not what we're doing with actual Fibonacci, where we're adding all the pieces up, but our analog of evaluation for Fibonacci would be, oh, you get that f of 1. Right? That is the normal form, right, that we would get here. Does that make sense? With our standard evaluation process, if we say these are the transformations we can do, we will end up getting that f of 1. Right? Because we're doing the first, the way our standard evaluation works is it gives the first transformation that applies. Does that make sense?
Yep.
Okay, so now notice that, well, this is one where we did deduplication, where, you know, where we can count paths, but where we didn't actually enumerate all these cases. Okay, so, but I think there was an earlier comment. So do you understand, do people understand what we mean by, let's see. I mean, the whole point is we have a different evaluation scheme. The evaluation scheme that we will be using right now is a single branch down here. Now, there is a trickiness because there are two pieces to that evaluation scheme. One is the recursion through expressions, and the other is a reevaluation. What we're seeing here is something much closer to reevaluation. And what we're seeing in the recursion through expressions is something much more like if we have, let's say, a hypergraph and we have multiple places we can update it, the recursion through expressions is saying, let's do that update, then this update, then this update. Does that make sense to people? Okay.
Do we understand what
we actually have to get some interaction here. So
yeah, my first question is, like, what is it that we think that we can get if we have let's say we have a multi-evaluate function?
Yes. Let me enumerate the goals. I thought we already did this, so I'm a bit disappointed that we don't seem to have the document from where we did this. Okay. First thing is different types of problems being represented naturally. Okay, so an example is logic programming. Okay, where it's like state a goal, given a goal and certain moves, you know, can you reach a conclusion, right? That's one case, being able to represent that naturally. So let's list the things which are like that. NP problems, things that are generally of that character. Theorem proving, okay, same story. Theorem proving, we've got chemical synthesis, we've got a bunch of these things where you basically give it where you give it a set of moves and its goal is to find a winning path. Does that make sense to people?
What about something like a SAT solving problem?
Yes, that's the same thing. I mean, that's in the category of, you know.
Well, I mean, what would the moves be? I don't know. I mean, maybe just like setting some variable in some ways. Maybe
I think so. I mean, you've got a tree in the SAT solver. You've got a tree of possible values for all those variables, and I agree that. Go ahead.
But one thing, like logic programming, they migrated away from their own unification algorithm and started to use linear programming and other efficient solvers.
Absolutely.
a lot of declarative functions where you give a
Yes.
goal and we solve it. And for
Yes.
SAT solving,
Yes.
we go straight through in many cases and do not use a SAT solver. More efficient. We can even count some of these things.
Yes, absolutely. Okay. What do I think this architecture is going to look like? Okay. I think in the end we'll have a multi-evaluate, and in multi-evaluate you will be able to write in the style of logic programming. You know, you can figure out the 8 queens problem by just giving the moves and the goal. See what I'm saying?
Okay.
Now,
And
how do we
the
actually
idea this would be
implement
like,
that?
I mean,
and if you, I didn't do much of this, but you had to give cuts and other things
I'm
to
aware.
guide it. Okay.
Yes, I'm aware. I know. The point is, and some of that stuff, right? So okay, let me the whole, okay, let's just give the bigger picture for a second. Okay, so one thing is you're finding one path. Okay, that is the traditional version of this kind of non-deterministic computation. You find one path. Okay. Okay, what are some other examples? Another example is another type of example, another type of thing
In
is more.
optimization, you find the best one. So you've
Yes.
sorted them all and ordered
Okay,
them, and
all
you
right,
want
okay,
to
so
find
you're
the best
right.
one.
You're right. So one thing is one thing here that we might list is, you know, find a path with a property, with a locally determinable property. Okay.
so by the way, I mean, is the basic point of that category just that, I mean, I don't know, there's a whole, I mean, like Roger was saying, I mean, we have like, you know, probably several different solvers. There's the linear programming stuff. There's the other convex optimization stuff. There's SAT solving. Is the basic point that there be one function that in a similar way to how solve, you know, I think now we'll call linear programming stuff if it thinks it's appropriate, you know, you have some standard way of expressing the problem, and then it will kind of figure out what
Yes.
type of solver and it
Yes.
will translate it
Yes.
and so on.
This is just the starting gate, because this is the very traditional limiting case of multi-computation.
Right. I'm just saying though, I mean, I think that already is that would be a very cool function to have. It's also probably be fairly complicated. And I think the design of how you would actually specify things. Well,
I agree.
yeah, whatever.
I agree.
I mean, that, yeah.
I agree, but we could imagine, okay, the function that we can imagine doing is a pure pattern matching function, right? So in other words, the thing would be, let's say it's called multi-evaluate. It won't be called exactly that because it needs, I wish we had the notes from the previous time. I'm really upset that we don't have these. Maybe somebody could go back and try and find this. So, you know, it's going to be a set of rules, basically. It's going to be some set of inits, and that will be generating essentially this kind of thing internally. Conceptually, it's generating that kind of thing.
Okay, here's the thing though, right? I think that the much more useful function is the one that conceptually is doing that, but actually it's translating it into a SAT solver problem.
Absolutely,
right?
Absolutely. Because what I'm going to explain is that then what we have to do is there is an observer here, okay? And the observer, this is the space of everything that can happen, the full game tree, okay? The observer, and I only got through the very first part here, one of the most trivial observer is an observer who only notices the path that has a particular property, okay? So another possibility would be essentially the probabilistic programming case, where the observer, you know, basically is just measuring the probabilities for lots of outcomes. And then the other cases, which I admit are more complicated, are the cases that are like quantum mechanics, for example, quantum observers, which is a different kind of observer of the same type of thing. It's an observer, you know, it's different reference frames. It's observers. Okay, so I mean, part of the motivation for this is I've got this big list of types of systems that I think can be modeled with multi-computation. But what you get out when you model them that way, let me just pull that list up. What you get out when you model them that way is not, okay, let me give some examples here. So let's see. I need to go find this. Hold on 1 second. Okay, so this was my list. Metamathematics, chemistry, molecular biology, evolutionary biology, neuroscience, immunology, linguistics, economics, machine learning, and distributed computing. Okay. So what does one imagine doing here, right? So in molecular biology, what I imagine, oh, what the heck? You know, this is a particular model for what's going on in molecular biology, where basically what's happening is those events are interactions between molecules, where, well, this particular one isn't very interesting because it's consuming one molecule and producing two molecules. But I could have another one here where it's consuming two molecules and producing two molecules, let's say. And the whole point is that there are different things you can observe about what happens there. One thing you can observe is the concentration of a type of molecule. Another thing you can observe that I don't understand as well is various motifs in the space-time structure, so to speak, that may turn out to be significant. So go ahead.
You are kind of thinking, I'm guessing that you are thinking that one would, behind the scenes would be something that's very efficient at sampling this or getting sort of a path with a particular
depends
property.
on the observer. It depends on, I mean, you know.
But so it's a different style of programming, basically, for certain classes of problems.
Yes, but the whole point is that, okay, look, what we think happens in the actual universe is that there's a ridiculous amount of computation going on under the, underneath, so to speak. And we, as observers, are computationally bounded observers that coarsely sample all of that computation. Okay. Now, it turns out that there's a way to do better than just doing all that computation and sampling it. It's things like the laws of physics, right? Things like general relativity are a way of jumping ahead and not doing all of that underlying computation, because most of that underlying computation is completely wasted on us. You know, just like most of the motion of molecules in a gas or in a fluid, for example, is totally wasted on us. We just don't care. We only look at these large scale features. Okay. I mean, the somewhat more controversial thing that's coming out is that's probably true of mathematics as well. That is, that a lot of what happens at the level of formalized mathematics and axiomatic kinds of processing don't matter for lots of mathematical purposes, just like it doesn't matter what the molecular dynamics of a gas is for lots of fluid dynamics. But the issue here is to have a model, an underlying model that is this multi-computational underlying model of all those possible, fluid dynamics configurations. But the thing we sample ends up being at a much higher level.
So maybe kind of an easier. I can see that maybe there's a class of problems that are now easy to formulate with what you're.
Exactly. That's what I'm saying. Yes, that is exactly what I'm saying. And I'm saying that those include some classic ones that we know very well, that we don't have a great, like logic programming, for example. We've never had.
There's also sort of agent-based.
Yes, agent-based models are the same type of thing, except agent-based models, what people do, one of the points of this multi-computation idea is, rather than doing probabilistic things where you say, well, the agent might go left or right, what you say in the core multi-computational model is the agent does all of those things. And we are merely sampling that space of possibilities. We are sampling the overall behavior of the system. And in quantum mechanics is really important, the difference between the, what's happening inside is there's sort of an integrated thing that's happening inside, and then you sample it. So quantum mechanics shows one that sampling all the time is not the same story as sampling only at the end.
But Steven, on the other hand, what you're saying here with respect of multi-computation sounds a lot like the ergodic hypothesis. So that might break sometimes. Like the fact that sampling all the possible states with the right weights is the same as simulating the microscopic interactions.
Yeah, right. Look. This is not. Yes, look, the ergodic hypothesis is an utter fail for playing chess. Right? There is a particular path that gets you to checkmate or whatever, right? The ergodic hypothesis just say, oh, all the paths are the same. Clearly not true in that case, right? So it is not the case. I mean, for some of these models.
So I don't know what, I know what an ergodic process is, but what's the ergodic hypothesis?
Okay, so the idea is that the ergodic hypothesis is a standard concept in statistical mechanics that says that if you have a gas, for example, you can look at a particular gas with a particular configuration of molecules, and you can see the time evolution of that gas. Those molecules will bounce around. They will take on a whole series of configurations. Okay, the ergodic hypothesis says that the series of configurations they take on is distributed the same way as the set of all possible configurations in the ensemble of all possible arrangements for the gas.
Right. So when you study random processes, you very clearly delineate there are some that are ergodic, but some are not.
Yeah, right, exactly. And I mean, the ergodic hypothesis is very, in its original formulation was vastly more complicated because it was not dealing with discrete systems and it had to deal with, bins and all sorts of issues about the continuum and so on. The ergodic hypothesis in a discrete system is a very straightforward thing. I mean, it's like you just look at, to give a trivial example, right? You can just say, you could just say something like nest graph of, I don't know, something like, I goes to mod I squared, comma 77, I goes from 0 to 76 or something. That's not what I wanted to do. I wanted to say, no, I just want to say graph here, don't I? I just want to say graph of that. Sorry, I meant this. Okay, so this is a non-ergodic critter because look, it's got these things coming in like this. If this was an ergodic critter, what would happen is it would just be a single cycle with everything on it. That would be an example of an ergodic, that's an ergodic discrete system. This is not.
I see.
Make sense? And the thing that's tricky is essentially this is now, I think, not so relevant to what we're talking about, but, essentially the proofs of the fact of how continuum behavior comes out of discrete molecular dynamics tend to depend on things like ergodic hypotheses. But they don't really depend on that. This is a long story. This is irrelevant. I mean, this is a whole story about computational irreducibility and observers and computationally bounded observers and what you can assume about randomness when you have a computationally bounded observer of a computationally irreducible process. But that's basically saying the bottom line, the net of that whole story is, if the observer is computationally bounded, then the things you observe, when you have a very complicated system that builds up a whole bunch of stuff like this, when you have a computationally bounded observer, there are certain, I claim, inexorable features of what a computationally bounded observer will observe, which can be deeply shortcut with respect to all of that microscopic dynamics. Okay, even though the description of the model may involve describing the microscopic dynamics, if all you want out is the result of a coarse-grained, computationally bounded observer, then there is a faster way to get that result than going through all the microscopic dynamics. But if you want out is, what is the correct series of moves to make for a chemical synthesis to get this particular output, or what is the best path for, doing whatever, then you don't get to have those optimizations. Essentially the claim is the laws of physics are an optimization with respect to multicomputation. The laws of physics are, for purposes of a certain type of observer, are a dramatic compression of all this multi-computational complexity underneath. Okay, and what I'm imagining is going to happen here is that we are going to have a language for the observer. And that language could say, what I want out is the best path, or the path that achieves this goal, Or what I want out is the probability distribution of all paths. Or what I want out is this or that. See what I'm saying? And that observer, or I might want out, and this is again something we haven't described, is the series of things, the time evolution of what you get from a series. So reference frames here are defined as foliations of this graph, of this multi-way graph. Okay, and so a foliation is something where you're making an equivalence class and you're saying this, and this. Those all correspond to the things I'm sampling at this particular time. Does that make sense?
Mm-hmm. Yeah. I mean, anyway, the reason why I was mentioning ergodicity, and I think you enlightened some stuff here, is like there is a very deep connection between the breaking of ergodicity, glassy transitions, and NP completeness. And so maybe we're actually onto something here. With
no, I understand that well, Carlo. You're right. Yeah. The way that, okay, so if you want to think about it in terms of spin glasses, for example, okay, you can think about, I mean, in you know, an NP problem, for example, for a spin glass, the ground state of a spin glass is, to find the ground state of a spin glass can be thought of as a, as an NP problem, NP complete problem, actually. And that you can think about that as, you're flipping spins deterministically. You are treeing out all the possible flippings of spins. And the path, one of those paths of flipping spins in a certain way will be the ground state. That is Roger's best path here. And the fact that that best path is the fact that that corresponds to an NP complete problem is, because that treeing out is like a general, non-deterministic Turing machine, a general multi-way Turing machine. That's really what it comes down to. But what you have to do, I mean, this path, just to remind people, this thing is, let's see if I can pull one up.
Yeah, but the really interesting the physically interesting stuff happens when the system itself has trouble computing what the ground state is and gets stuck.
Of course, right. So, the physics does not win. Look, yes, and the reason it gets stuck is that, okay, so I mean, this question of does it flip this way or that way, eventually the energy differences, it's the same story as with finding local versus global minima, et cetera, et cetera, et cetera. How do you do that? Can you find, by saying, let's say, for example, we take gradient descent in this tree, right? We say, as we go through this tree of possible configurations, let's always pick the branch of the tree that is locally going downhill. That's essentially an implementation of gradient descent in this sort of semi-discretized system. And we know that will often not get us to the global minimum, right? Instead, what we have to do often is we're going down the tree and we have to backtrack. We could use simulated annealing if we wanted to think about it probabilistically. We backtrack up the tree and then we keep going down again. And there will be a particular path that is the winning path. And that path will not be findable necessarily by any method that involves just local moves, if that makes sense. And it's the same problem. So these are non-deterministic, these are multi-way Turing machines. These are Turing machines that can make more than one move at each step. And again, we have this question, if we're doing a deterministic computation, can the Turing machine solve the, what's the best state of the Turing machine? There's one path that gets that. And we can ask the question, we can ask questions about the probability distribution of Turing machine things, etc. I think yes, the example of spin glasses is a fine example of where you can absolutely describe the partition function of a spin glass in terms of a set of moves about, flippings of spins and so on. And you can ask the question, this is, what's interesting about multicomputation is that usually in statistical mechanics, all you say is we've got a partition function for a spin glass. That's it. and you say in the canonical ensemble where you just have a temperature, there's a certain weighting of the configurations of the spin glass. What multi-computation is doing is it's also talking about the time dynamics of the system, which is not something you usually do. I mean, usually in a spin glass, the best you'll get to is Glauber dynamics or something.
Yeah, but that's the exact, like some features, some physical features cannot be described solely but by the the static of the spin glass. Basically, there is something about the fact that the system is very hard to solve that shows up in the physics, and the system itself cannot do the computation.
Yeah, right.
It's going to work.
Yes, it's the same story here. I mean, this is an exactly equivalent setup. And I mean, by the way, yeah, there's all kinds of examples of this, but I think that's not, I mean, the traveling salesman problem is absolutely a fine example of, well, actually, I'm not quite sure how well formulated it is here, but to just continue sort of my vision of this. So there are a set of, to me, the question is, can we represent the set of moves by purely symbolic transformation rules for symbolic expressions? But there are many possible ways those rules could be applied. It's a replace list type story, right? So, replace list could tell us f of, blank, I don't know what it is, x blank, x, y double blank. That's that going to, I don't know, x, y, and then we're saying replace list here, f of a, b, c, d, that's giving us all the possibilities there, right? That's different from replace, which just picks the first possibility. Why is this not finding more cases? Am I confused here? Why is
Probably need x __ 2.
Oh, yeah, right. Okay, there we go. Okay, so that is an example of a very trivial multi-computational thing, right? It's finding these many cases, right? We don't have a replace list that goes all the way down through an expression. And part of the reason we don't have that is we don't have a good way to knit together those pieces, because what we're seeing here is this is a way of knitting together. I think I have some better examples somewhere, and I wish I had the previous previous notes. We really should never let this happen, of doing these meetings without previous notes. Really shouldn't let this happen because we're wasting a huge amount of time here. Well, let me see if I can find dear. I'm looking for, those are all, it's not interesting. Well, it's going to be relevant in a minute, but, well, okay, so here are some examples. What is this an example of? No, this is still a one-to-many transformation.
Are you looking for an idea of how to specify that multi-evaluate here, or
yes,
are you looking
that's
for
what I'm looking
an idea of applications, or what?
No, I'm looking for design. The objective is very straightforward, okay? Although not easy. I'm looking for a way to specify multi-evaluate, and particularly this observer piece, that is a nice, robust thing to do that will let us achieve a bunch of different goals here, okay? And right now with this, what this is operating on, this is saying, this is a bunch of transformation rules. And for example, for combinators, we know what those transformation rules are. And we know what, they're transformation rules for expressions. And what we're saying is we want those transformation rules to be applied in all possible ways. Those rules, in general, will use more than one expression at a time. Do you see what I'm saying?
Mm-hmm.
Right? These events don't necessarily have to, I'm really kind of annoyed that I'm not finding, hold on, maybe this has some examples here. Okay, well, there's a trivial example of a token event graph with, I mean, this is with token event graphs, which is not the right formalism. It's only part of the formalism, but here we've got, this is a 2-to-1 rule. See what I'm saying? Mm-hmm. And in general, what should happen here is that what we're going to do is we're going to say, these are the states, and we're applying in general, these rules will say, well, let's see. Yeah. This is the issue. The issue is tokens. Okay. In this model, in this setup, we are just looking at disembodied tokens. Okay. In general, what transformation rules that we have in the system do is they look at subparts of expressions. Does this make any sense? Let me try and give an example. Okay. Okay, so here we've got a string replacement rule. Okay, and this string replacement rule, BB goes to A, takes a subpart of that string and replaces it. Okay, but the subpart of that string is embedded in the whole string. Am I making sense?
Right.
Whereas here, these tokens, what we could do with this string if we wanted to, but it's very unnatural, is we could break that string into a linked list, and every character is its own token, and every one has its kind of connection, okay, next to it. Do you get what I'm saying?
Yep.
Okay. And then we could use the same idea that BB goes to A is two tokens going to one token. Do you see what I'm saying?
Yep.
That's rather unnatural. It's not what our pattern matcher does. Our pattern matcher instead can take the BB conceptually that is embedded inside an existing thing and make the transformation on it. So the first question is how to get the so that's what I'm imagining. Somehow there's a sea of expressions that's being generated, and the inits are an initial sea of expressions, and the rules are taking subparts either from a single expression or from multiple expressions. And maybe that's an incorrect way to think about it. Maybe we just want us always to think about, well, no, I think that's the right way to think about it. It's taking this multiple subparts from different expressions, and those rules are saying this is the transformation that's going to happen, right? We can think about that, the multiple subparts as tokens, but those tokens can either be one of the important things is that you can have two different expressions that are sort of swimming separately in this set of expressions, and you can combine them together by a rule to generate a new thing. Does that make sense?
It sounds like you just want tokens to the expressions.
No, because no. The whole point is tokens are embedded as they are in strings. Now you can say, oh, in principle, you can make a linked list, right? But I'm saying, I think there's another idea that's needed that involves the pulling out of tokens from things. We have the exact same issue in theorem proving, okay? When we state the application of a theorem proving rule, we have to give this very ornate way of saying, in a theorem proving rule, when we apply it, we have to say it's applied to part number 231 of this expression and part number whatever of this other expression, and then we glue them back together in this way, okay? Now, we could say, shatter those expressions into tokens, and then we don't have to say it's part number 231 of this expression. It's just a token. The problem with that is we have no idea where those tokens go. They're just free-floating tokens, and we've lost a ton of information. So let's look at it a little bit. Does this make sense to people? Should I give a more explicit example of the theorem proving case? Would that be helpful?
No, I see what you mean. I mean, the main problem is that it's hard to turn expressions into tokens.
Right, but I mean, even in combinators, right? So let's remind ourselves again: are other people following this or not? Because I want to make sure people actually are following. Yes, no, maybe.
Yes.
Okay. Okay, so in combinators, a very pure version of this, what we have are these weird tree update events. where what has to happen is, I don't know where we have an example of this, but you know, here we go. This may be some part of this. These are these weird pullback events. Okay, so remember, in a combinator, you are making a transformation. You know, you take this tree, and the transformation rule, and a combinator is an expression, and the transformation rule rewrites a part of the tree. That makes sense? Roger, everybody else, you're on board, you understand what's going on.
Yeah.
Right? Okay. The tree that is rewritten could be thought of as a token. Okay. The subtree that is rewritten, the rewrite, you know, the combinator rule, S of XYZ goes to whatever, is essentially ingesting 3 subtrees as tokens. And it is producing 4 subtrees as output, 4 tokens as output. But it's very important that when those tokens are ingested, they come from a particular place, and they are going to be reinserted back into that place. They could be free-floating tokens, but then we have to have all kinds of weird connectors that reattach them after their rewrites. Does that make sense? Max, you understand what I'm saying?
Tokens refer to each other. I mean, that's more natural way to think about it.
I don't think it's a more natural way to think about it. I mean, that's what you do in the case of, look, in the case of a linked list, okay, you can represent a string as a linked list, right?
Sure.
But in order to do that, the linked list has to, do people understand this idea? Yes, no, maybe? Let me show that idea. Okay, so this is a bit more extreme, but it's basically the same idea. So this is a string transformation rule, okay? And in this case, the string is being represented by a hypergraph, and rather ornately, you know, the B is a loop and the A is a non-loop. Make sense to people? Yes? No? People understand? Do I pick on somebody and ask if you understand? Okay, Carlo, do you understand?
Yeah, I think so.
Okay, so what's going to happen here is there is a rule that basically just talks about but effectively there is a reattachment. Every one of these, every node here implicitly has a name. It's a graph node.
It's
right?
not a node, it's a hyperedge, and the A is actually to the right on the bottom. This is just a connecting vertex.
Okay, fine.
So the connections between letters in this case are represented as shared atoms in different tokens. And so this vertex in the middle, that's a connection between A and B.
Yes.
There's one thing I'm confused about. You can definitely create a graph that cannot translate to a string, right? An hypergraph.
Oh yeah, absolutely. Yeah, these are very special hypergraphs that are specially built to be like linked lists, right? And I mean, the whole point is that in a graph, it is somewhat natural to have these reconnectors, because we're used to the idea in a graph that there are implicitly names underneath, okay? So in an expression, we don't have that. In an expression, we just have this tree structure. We don't name the tree elements. We just write them out in the way that we standardly write out a tree. In a graph, under the hood, there are names for every vertex, right? And so when we reattach into a graph, there is a, you know, we just have to name the vertex and we say where to reattach. In a tree, you know, we can say where to reattach by giving a part number, but the whole point is the free floating token. Okay, a free floating token, and it reminds me a little bit of the immune system and other things. A free floating token could in principle have an address on the side of it, which says, here's where to reattach me. Okay, and it may be that that's the right conceptual way to think about this, but it sure isn't. It would be, well, okay, so the first issue is when you are applying all possible transformation. You've got a collection of expressions, and you're applying all possible pattern transformation rules. And those transformation rules could involve subparts of more than one expression. Does that make sense to people? Do I need to explain that further?
Yeah. So I feel that I understand. I think I understand where you're trying to go. I'm just, can I try on you, test it on you?
Yeah.
So if this wasn't rules, if this was like a non-deterministic finite state machine, then we could still have an init, which could be a whole set or a single state, doesn't matter. Then we have what you call observers, what I would call output equation. But what is evaluation? That's what I don't get. Is that like it's
okay? So evaluation is the running of the finite state machine.
But it may never stop.
Absolutely, absolutely. Okay, this is a very important point. This is a very important point which I was not mentioning yet, and because I forgot. Okay. One feature of our current evaluation scheme is that it uses normal forms. Our model is there's input and there's output, right? So x equals x plus 1 just blows up in our current evaluation scheme.
Yeah.
Okay. The universe, we firmly hope, at least for the time being, doesn't terminate, right? Yeah. It's just an ongoing computation. And we are sampling that ongoing computation. Now, in our evaluation scheme, we have in one, out one, etc. We have this notion of input, crunch, 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 output, right? One of the features, there are multiple features of this multi-computation idea that have to depart from our current evaluation model. And one of them is, yes, that's the whole point. That's the whole point. That's what this reference frames thing is all about. There are a series of snapshots you can take, right? In the universe, there are a series of time steps. There are a series of times at which you sample the state of the universe. So similarly with your finite state machine, absolutely. What one will be asking for is not, does it go to an acceptor state? One might ask that. That's one of these cases.
Sure, absolutely.
Right? Does it go to an acceptor state? Yeah.
What is it we want to ask for?
Well, for example, in a finite state machine, or let's say a Petri net, one step up from a finite state machine.
Or Bishi automata,
which
is Bishi automata or omega automata. These are that can go on forever.
Well, I mean, a finite state machine can go on forever. You just keep circulating around. I think that's yeah. I think.
Sure.
I mean, I think that's what. I've used the term finite state machine to represent the thing that I think other people call Bucci automata, which are just things without acceptor states.
Right, exactly.
And they just keep flapping around. Okay, yep. So I've used those a bunch in, like, for example, in cellular automata, there's the following result. In a one-dimensional cellular automaton, after t steps, the set of configurations that can be reached is determined by the set of possible paths through a finite state machine.
Right.
Okay.
But you're trying to generalize that finite state machine to expression and transformation, which has a similar non-deterministic character because they can apply it multiple places and stuff.
That's exactly right. Right. So the whole point is that, okay, you ask, what do you observe about the finite state machine? What do you observe about the Petri net? So one thing you might observe.
What is the out from this function? What is the
That's the whole point. There isn't an out. That's the whole point. That's why this is a paradigmatic difference, right? There isn't an output. It doesn't work that way. The observer can observe some definite thing and can deduce a definite thing from the behavior of the system. But the observer doesn't say, clink, here's the output. Right? The observer can have an output from the observer, but the system itself is still running.
For me to test, because observer means a different thing in other contexts. But I think what you mean by observer is a function of the state. Is that right?
Yes, that is correct. But it might be
that's normally called output equation in control. Observer is one that actually, given that what you call observer or the output, you try to infer the state.
Fine,
just,
fine,
it's just
fine. I mean, that's interesting. But I mean, I think the point is that what I think is the case in multi-evaluate is that that observer function, there's probably a multi-evaluate and there's probably a multi-evaluate list or some such other thing, in which both one of them says, given this observer, I just want this this kind of I want the path with this property, clink, one result, right? Another possible thing there is
also that somehow that tells you when to stop. Then if I find a path.
Yeah, exactly. I mean, look, the whole point is this, a big part of this story, wherever I had those pictures, is where do I have those pictures? Oh dear, where did I have those pictures? I had some pictures. Oh, I don't know where I put them. Who knows? Oh dear. That's what we got right now. Okay, so what I was trying to show was maybe this. Okay, so again, another thing which we haven't talked about properly is this notion of causal graphs. Because again, in what we do normally, we have a deeply impoverished view of evaluation. All we see is the input, grind, the output. We do not see the update events that happen during evaluation. That was what Trace tried to do back in 1991. We haven't got a good way of exhibiting, what is the series of operations that we do in an evaluation. You see what I'm saying? Okay, right. One reason why we have trouble, okay, is that unlike a procedural language where there's a program counter and where it's just going through and it's got this state, this state, this state, this state, our notion of states is considerably more complicated because of recursion through expressions. Does that make sense?
Yes.
So, what do you show as the state? What you have as the state is both the here's this thing, let's say you have a procedural language that's got 4 variables, x, I, j, k, or whatever it is, right? The state is just the values of those variables. But for us, the state and the program counter is just grinding down. But for us, the state is where did the evaluator get to in recursing through this expression, among other things. And so in this kind of representation involving here, we are kind of showing the actual evaluation, the moment of evaluation, the event where something happened, right? That's part of the data structure here. Does that make sense? So part of the story, and one of the things that's come out of the physics project, is the importance of causal graphs that give the causal relationship between successive events. That turns out to be an important thing. But we have none of that information in our current evaluator. We're not storing that information. We don't care. We're just going grind down a particular path and saying what the answer is. Why does one care about these? One of the issues is once there are multiple paths, for example, the composition results that you have are much more complicated. It's no longer the case that you can just say it's this set of functions composed with this set of functions. It's a more, it's a whole giant monoidal category story, or however you want to think about it. Does this make sense? I mean, in other words, okay, so the whole point is there is an evaluation. I think we've looked at this before. This is super frustrating for me. It's just ridiculous. we've looked at this before. We talked about this notion of computation objects and things where we're actually storing this thing. I don't know where my notes about that are, and we really need to find that. And we're not making progress here. I mean, what I had wanted to do was, part of the story is you've got one of these things here, and you're asking, what are some reasonable kinds of ways to foliate what's going on here? Does this make any sense? Does anybody understand what I'm talking about, or is this hopeless?
Yeah, definitely. I mean, you're talking about properties essentially.
Maybe. Look,
it has the evolution object. And then
let me be clear. There's several things that are wrong here. Okay, token event graphs are not enough because they do not encode the information. Okay, in the case of the physics project, the tokens are hyperedges of a hypergraph. Okay, and the information about which tokens are ingested in an event is not. There is an additional piece of information, which is how the tokens relate to each other to make a spatial hypergraph at a particular moment in, but that is a subtle thing.
That's actually contained in the token event graph because tokens contain the atoms.
Only in that case do they contain. The tokens contain the information because the tokens in that case are hyperedges with named, elements, right? They know how to knit themselves together. See what I'm saying? If they are fragments of expressions, they do not know how to knit themselves together. X plus Y has no idea how to knit itself to some other expression because it doesn't come attached with markers on the side. A hyperedge, because it is a hyperedge between, atoms, between named elements, between named atoms, it intrinsically knows how to knit itself together. Does that make sense?
Right.
Whereas a random fragment of an expression does not know that, right? So we'd have to give it extra wrapping to tell it how to do that knitting. That would be one possibility, one possible design approach. I don't think it's the right approach, but it's one possible approach, is that there are these expression fragments, like let's take the example of the combinators. We could name in the combinator tree, okay, we have your average combinator tree, wherever there's a combinator tree here. I'm sure I've got combinator trees. There are some good combinator trees, okay? Right now, we are not naming the nodes in those combinator trees. Do you see what I'm saying? All we're doing is we're saying, let me explain this because this is a useful thing to think about. Okay, everybody understand what this is? Yes, you understand what we're looking at? Anybody not understand what we're looking at? These are tree representations of symbolic expressions that correspond to combinators, yeah? Like, is Christopher with us here?
Yeah, I'm here.
And you understand what we're seeing here?
Yeah, I think I know what those graphs are.
Okay. All right. So the point is, when we make a replacement for a subtree, all the numbering right now, we are not naming the nodes in this graph, right? They are just given tree numbers, basically. This is a symbolic expression. So when we detach this subtree to ingest it in our rules, the reattachment is a complicated issue. That subtree doesn't have a bunch of numbers for every element in the subtree.
So what information is contained in tokens in this case? Because tokens is not the entire subtree. It's just the root of that subtree.
Well, yes, you could say that. But again, then what you're saying is we could make a token here that is the representation of the root node together with its tentacles, its numbered tentacles that say how it connects into the rest of the thing. Right? That will be the analog of the hypergraph case. I want to explain for people who haven't been involved in the physics project, the next really complicated issue. Okay? the let's say that we've got a bunch of tokens, right? And we want to knit those tokens together into a state. Like, let's take this example here. We've got different subtrees being rewritten, et cetera, et cetera, et cetera. We've got a certain set of events that have occurred. Now we want to take the token collection that exists at that particular, after those events have occurred, and we're going to knit that back together into a state. Here's the tricky thing. There isn't a unique, the question of which events have happened is not a unique, there's not a unique ordering of events, right? Roger, do you understand this point? So the issue is there can be, let's take even this picture here. These, well, I'm not even sure, I have to look more carefully, but my guess is those two events are space-like separated. Do you understand this idea? Roger? Are you with us, Roger? Oh, for goodness sake. Roger seems to have dropped. Okay. I think this meeting may be doomed. Okay, do other people understand? Christopher, do you understand this idea about space-like separated events? That is, events that are not forced to occur in a certain time ordering. They're anti-chains. They're anti-chains in the partial order, right? And so the tricky thing is that the reconstruction of states is not unique because it depends on how you foliate the causal graph.
Well, what do you mean by the reconstruction of states?
Okay, so the tokens are just hyperedges, or in this case, they are roots of subtrees. Okay. So, let's see, what is this? This might be the notebook. Well, that's not useful. I need to know if James is giving me a notebook direction. I need to know the and this is this. No, this is not the relevant. If this is the notebook you're thinking of, this is not the relevant notebook, I believe. Well, it's something. Yeah, it's part of it. I'm not sure. Anyway, the point that I'm making is a state, like the state of this hypergraph, is something that corresponds to a certain set of tokens which can exist at the same time, if that makes sense. And it's not the case that there's a unique set of tokens that can exist, quotes, at the same time. It depends on how you foliate this graph. Right? It depends. There are many different choices of sequences of anti-chains. I think everybody is lost. Is everybody lost? The whole point is, look, you've got a bunch of hyperedges. I think Max at least understands this. You've got a bunch of hyperedges. Oh, yeah. They were generated at different times. They were generated, and the whole point is you can make a foliation of this sequence of events where you can say this set of hyperedges can exist at the same time. It is not unique. There may be a different set of hyperedges that exist in a particular time. So it isn't the case that you can say, as you can in our usual evaluator, this happens, then this happens, then this happens. There are many different choices. That's essentially relativity. That is telling you there are many different choices of simultaneity surfaces.
One token might exist in multiple states.
Yes, well, that's true too. But the whole point is the knitting of tokens into states could be, okay, it could be the case that it's an afterthought. Okay, that you've got all these tokens and then later on you knit them into states, later on, you figure out how you're going to observe them, because the observer is effectively making other equivalence classes. Does that make sense? When the observer is, I mean, statistical mechanical version, when the observer is doing coarse graining, the observer is effectively making other equivalence classes. I think there's some interesting comments on our live stream here. Maybe we can look at these. Marco asks, is a normal form a black hole? Yes, it is. Richard is saying, for causal dependence tracking, you need to associate variables in the true-false branches with those in the condition. Oh, that's commenting on the if statements. And the comment is, there's a different way of treating that for static versus runtime analysis. Yeah. I kind of think static analysis is closer to our expression recursion, and runtime analysis is closer to the reevaluation recursion.
Analysis of what?
Of these evaluation processes. I mean, in other words,
a static analysis sounds like you would try to prove something from the rules without running the system.
Well, it depends. If you've got a straight line, if you've got a once-through program that doesn't have a loop in it, you can still have a whole nest of if statements where, you know, like one of those, you know, Galton board things where the ball can go left or right at every step. You can still have many paths through the ifs. And let's see. Marco is commenting on various things about graph branchings. Yeah, Satori is commenting, basic multicomputation is about having a way to describe paths of the multi-way graph possible pattern matching. Yes, that's pretty much right. Means ends analysis. Yes, I think that's related. That is the that term, the means ends analysis is the same type of story as we're talking about here, I think. So Tori is commenting, multi-computation for finding a good decision tree. Less so, I think. Let's see. Runtime, instead of going one transfer rule at a time, you're looking. Right. So Marco is commenting, and it's a pity Roger has left, that the NDFA to DFA transition, right, is a coarse graining transition. Right. So the people know the NDFA, the Myhill-Nerode theorem, or whatever it is, the one that will translate from a non-deterministic finite machine to a DFA, that is essentially a coarse graining of states story. Because what you're doing is you're taking coarse graining or equivalencing different states together, right? Does that make sense? No? Does anybody understand this? Come on, I know people know how this NDFA to DFA transformation works. Christopher, you know how that works.
Should we try a visual example?
No, I mean, people either know this or they don't. I mean, I think Christopher certainly knows how this works. Yeah?
Yeah, I mean, I've seen this before at some point.
But the whole point is, in an NDFA, right, what you have is there are multiple possible, I mean, let's see if I've got an example. I think I might have an example from things I was doing just recently. Let me see if I can think of an example here. I think I might be able to do that with this may make a DFA. Look, the basic point is, given a state of a finite state machine, the question is, with a given symbol, can you get Is there just one way? Is there just one path with a given symbol, or there are multiple paths? It's the same thing as with a non-deterministic Turing machine. If there's a particular configuration of the Turing machine, is there just one next state or multiple next states? And the whole point is that for finite state machines, there's a construction that allows you to basically equivalence together. Well, let's see, how does this work? I have to look it up in oh, never mind, it's probably not relevant. Okay. Richard is commenting. Okay, I don't know what this is. More recent solvers use conflict-driven clause learning. I do not know what that means. Maybe with respect to SAT solvers, I don't know that. I thought that people were still using the Davis-Putnam thingy. Oh, this is an improvement in the satisfiability algorithms. Okay, that's kind of an interesting picture there of not sure how useful that is. I mean, that looks like a theorem proving-ish way of doing SAT solving. Let's see. Super optimization, Richard's comments, and people optimization, which usually involves SMT. Right. I mean, that's optimal. Yes, you're right. If we could do things, super optimization and so on, involving, just flipping around machine instructions and so on, that is exactly the type of thing that we would define rules for. In fact, I know that in a big one designer of microprocessor architectures used our language long ago to do essentially symbolic transformations on sequences of instructions and so on, using exactly that kind of idea. Okay, Marco is commenting. Okay, incremental heuristic search. I don't know what that is. In logic programming, it's very observer-like. I don't know what that is. Let me look that up. Does anybody here know what that is? I don't know what that is. I'm going to make a note. That's a thing to study. Let's see. Equivalence, Marco is commenting. Basically, the problem of equivalence of languages or grammars up to a certain tolerance. Yes, that's an interesting thing to think about. That's an interesting thing to think about, although that's complicated because, gosh, there isn't a good way. We've been interested in that problem because we're trying to find fast heuristics to determine, for example, whether the Wolfram Alpha parser can successfully parse something. Let's see. Okay, Richard is commenting, have an edge rule, apply rule predicates. Okay, this is a comment I need to parse more carefully. Have an edge rule and an apply rule predicate applied on some logic programming database as an initial state. There are abstract machines implemented using graph rewriting. Okay, so Richard is pointing us to a reference here about implementing logic programming languages by graph rewriting. Yeah, I mean, so that may be related to a lot of stuff that's been done on let's see what we've got here. Oh dear. was a file in a .gz.ps.gz format. Oh, look at this, very convenient. This seems to be a book about implementing logic programming languages by graph rewriting. Okay, I wonder what this is about. That might be relevant to us. Sounds potentially relevant. Graph rewriting, okay, term rewriting systems. I mean, graph rewriting, people often talked about this in terms of for combinators and so on. What the heck is all this? Okay, this looks relevant. Okay, that's term rewriting. Okay, those are expressions. Yeah. So, I mean, this may be what we were saying before, namely, you are rewriting graphs. See the advantage of graphs and hypergraphs over standard tree-like expressions is you can always, after you do any transformation of a hypergraph, you can always re-glue the result back into the hypergraph. Whereas, well, it's particularly bad for an expression if you are taking two parts of the expression. It's completely unobvious that the new piece that you get from those two parts can be re-glued. Yeah, that's a good point, actually.
Well, by what mechanism would you specify the two parts are being taken together, where you're not basically just saying that the single super expression is being transformed?
Well, I'm just saying that you can take two pieces, two distant pieces. Okay, let's imagine we have a soup of expressions. We have 1,000 expressions, and we're going to pick pairs of them to make transformations on. That will be an example. I mean, like what's happening here.
So number of outputs will need to be the same as number of inputs. So that because
why? No, if you're going to reglue them back into the same place.
Them with something.
No, but the whole point is, look, when you do a transformation, particularly on multiple inputs, and you get a different number of outputs, how do you reseat, the outputs back into the places where the inputs came from?
Right. Well, you can create new expressions which are not connected to anything.
I know, but that's not what we want to do. That's the whole point. We're losing something here because our standard evaluation scheme
we might want to do.
Right.
But we still need to put the sub expressions back. I mean, something needs to be there, even if it's just one symbol.
Right. So the whole point is for hypergraphs, or even graphs.
Yeah, this problem, we delete all the expressions.
I know, but the problem of how to reseat is solved because you know how the thing connects. This problem is solved because
we delete old ones and we create new ones.
Same difference. We know how to reknit them back into a state. Right? Whether the state has all new, fresh other hyperedges doesn't really matter. We still know the new hyperedge. We know how to connect it into the existing hyperedges.
Sure, but I think it's a separate issue because with a hyperedge we can just delete it and it doesn't break anything. With a sub expression we can just delete it.
That's a good.
It would be the same issue if you had hypergraphs where the vertex degrees were fixed to to like 3. For example.
Fair enough. Okay, right. For in a hypergraph we can just delete an edge and it'll still be a perfectly good hypergraph. And all will be okay. I think that's one of the reasons when I was doing trivalent graphs, that's one of the issues. That's one way to state what are the issues. I mean, this wouldn't work, e.g. in a trivalent graph. In a trivalent graph, there's a lot more constraints on what you can delete and so on.
Right.
Carlos sends something about zippers. What is this? This is just What is this? What is this, that thing?
Zipper is basically it's the data structure that comes out when you're trying to traverse a data structure. So basically, if you have you're traversing a list, the zipper of a list is two lists, the one on the left and the one on the right of the cursor.
Okay, what is it for a tree?
Well, it's funnily enough, it's the derivative of the tree in the type system sense, but it usually ends up, if it's a binary tree, it's two trees basically.
What is the relationship between zippers and tracelets? Anybody got any idea?
I haven't heard that term before.
So your claim is that a zipper is a derivative of a data structure in some sense. It's the type derivative of a data structure.
Yes.
I'm sorry?
Yeah, basically, yeah, the way to think about it is that if you look at, if you think that a list is like, it's like a series, right?
Mm-hmm.
You can sum it and basically you have this relation that looks like the geometric series.
Yeah.
Right?
Okay. Yep.
1/1 minus a, where a is the type. And so basically you can derive with respect to the type to a, which is the piece that you're removing, and you get two lists basically, which is the left and the right. And you can do this for binary trees and so on.
So one way you could think about a zipper then, if you use a zipper as input, it is like replace part or something. A zipper is telling you, like in our theorem prover, okay, what's the relationship to the theorem prover? In other words, is a proof, is a zipper like a proof? As in the sequence of things that you change to get to the result. And you could imagine feeding the zipper back in again and saying, these are the places to do the replacements at. Does that make sense?
I'm not sure. I mean, it's, as far as I understand the zipper, it's a much simpler thing. Like you're doing string substitutions. You have to, if you're doing something in the middle and you look at a string as a linked list, you have to keep both the left part of the list and the right.
I understand, but that's what's being said here. But I'm sort of generalizing that to say this is the trace of what, of where you did things.
Yeah. Okay. Yeah.
Okay. The port graph. Okay. Richard is saying in logic programming, his logic programming approach, the initial state is immutable. It says an edge exists at time t if a rule applies t minus 1. Rule applies at t minus 1 if the edge exists at t minus 2. Okay. Yep. The port graph framework. Okay, this is another thing that I don't know what it is. I have to look those things up. Marco saying the tokens represent the space-time you followed. No, that's not really right. The tokens represent pieces which you knit together to make space. Let's see. Richard is commenting the NFA to DFA is a power set construction where you get multi-states. Yes. What do rules look like in multi-evaluate replacement rules? Yes, they just look the same as, I think, my current thought is, but this is where I'm confused about the regluing of expressions, that they look just like current transformation rules look. Let's see. Marco's commenting, we get the same result as combinators by doing string writing. I don't quite think so. Maybe they're with parentheses. I'm not sure. Maybe Max knows that. Oh, and Richard's commenting, port graphs you can have labeled. Oh, okay, then I know what you're talking about. Yes. Oh, yes, I worked on those extensively before we invented the kind of hypergraph idea. There are, they are not as clean as hypergraphs in my experience. but it's basically you end up with a situation where, I mean, to give an example, if I'm not mistaken, and we haven't really followed these particularly. Hold on. Where is it? I had some whole giant can of worms here from 2006, it looks like, and of these things here, where you have, this is, I think, what you're talking about. These are graphs where instead of the edges being just, oh, I'm just an edge connected to this node, it's like around every node, there is a naming of directions, so to speak. And the main conclusion of this is it's very similar to what we're doing now, but it was just a little bit messier.
I mean, these are in between expressions and ordinary graphs.
What do you mean by that?
Well, expressions also have labeled ports because you have a head with labeled sub-expressions. But they're also trees. And these ones don't have to be trees, but they're also not completely structureless.
I wonder whether that actual copy works. Oh my gosh, look at that. Time warp. Let's see. Richard's commenting, hypergraphs is bipartite graphs where partitions for vertices and edge vertices. Yes. That I think is the same kind of thing as we have in these token event graphs, where they're the event nodes and they're the token nodes. Look, the stuff I'd hoped to get to, and we are running out of time here, is unfortunately this didn't quite go the way I was hoping it would go. So it goes. We're still in an early phase for this project. What I really want us to think about is, well, the regluing problem, the regluing of things back into, that's one thing. The question of what it is, what the language of samplings is, and then how do we write optimizers given, I mean, so in other words, one thing we could do is to say, let's get a computation object that represents a giant token event graph that's all been worked out. That is completely impractical for most cases. What is realistically going to happen is pieces of that graph may be generated, but then based on what we actually want to pull out with the observer, we'll end up with vastly different actual computations that we do underneath. Does that make sense to people?
Oh, there are really two pieces here. Is one, which parts of that graph you want to compute, and the second, which property of that we want to extract.
Yes, but some of that
pretty much independent.
Maybe. I don't know. If we're trying to do probabilistic programming, we're trying to construct a distribution over all results, right? Let's say we want to compute a distribution over states. Not tokens, but states, a distribution over states. Then I don't know what we compute. It's kind of complicated to know what we compute. That's a whole graph computation, but an approximate one.
Yeah. And you probably want to do sampling in some kind of clever way.
Yeah, you want to do some kind of Monte Carlo important sample type thing, probably. Whereas, you know, but the thing that I guess I was particularly interested in also is what is a plausible foliation, right? So these are total orderings, but those are foliations, right? And there are different, you know, they're different. That's a foliation, for example, right? That's a particular way of deciding how to sequentialize a series of events. Making sense? One question is how to describe these foliations, right? So in other words, if we have a family of foliations, how do we describe it? Okay, in relativity, we have things like inertial frames. That's a description of a foliation of space-time. The question is what to do in this case, where we have these different possible. Is this making any sense?
I mean, how do we describe it when we before it's computed?
Yes. How do we describe which foliation we want? Like, I want the inertial frames. I want an accelerated frame. I want this, whatever. That's what we could be describing in a spatially, in a system where we can lay out the tokens, where again, it's a little complicated because of branch-like separated versus space-like separated. But in the pure space-like case, we're essentially laying out tokens in space. And we're asking, or laying out events in space, and we're asking which events do we want to say, what is the ordering in which we are going to consider the events to happen? Right, and that's going to be relevant in, if we want a multi-evaluate list, that's going to tell us the time evolution. And by the way, for things like x equals x plus 1, or a non-terminating combinator expression, or I claim a bunch of things of relevance to molecular biology, immunology, a bunch of other areas, this dynamic thing of what is the structure of this graph evolving over time is kind of important, right? That's the thing we want. But it is evolving over quotes time, where time is defined by some foliation. But we have to have a description language for those foliations. Does that make sense?
Yeah. Yes, I think so.
Right. So in general relativity, that would be a gauge. Right? That's what you would call the foliation is, you have a shift and a lapse. What is it? Shift vectors, lapse vectors, whatever, which determine how you map points at one moment in time into points at another moment in time. And so the question here is, what are reasonable ways to do that specification? Just like for example, we have a very coarse thing we do. We have a recursion limit, right? If you recurse x equals x plus 1 enough, we just say, oops, we're stopping. I don't even know what the front for the recursion limit looks like. That is, if you have a complicated
that sounds like
recursion,
Marx generation.
It is, yes, it's something like that. Right. But I mean, this, this is right. So generations are one concept for a foliation. By a generation, we mean a maximal subset, a maximal antichain, if that makes sense. A maximal subset that can be simultaneously done. Right?
What do you mean? Generation is a number.
No. But the definition of what is in a generation, what events happen in a generation. Right? In order to decide.
But if you take all tokens, actually, no, it wouldn't necessarily be maximum subset.
Well, what is it?
Because in a state, you might have leftover tokens from previous generation.
Fine. Okay, but there's a definition, right? So, I mean, that's
there's a definition for generation number.
Okay, but look. So, I mean, the foliations. So one example is generations. That's one type of foliation.
The event order in this case would be monotonically increasing generation, which is a class of event orders.
Okay, but then so we can talk about foliations as basically their event orderings. But so what?
Well, there's a little bit more than that, because event ordering So
Yeah, that's a total order.
foliations are a list of events.
Right. That would give a total order. But what we want is a
exactly.
partial order.
Right.
By the way, another related thing with foliations is breadth first search and the different variants of breadth first search. Let's see. Iterative deepening is a foliation with respect to some heuristic that is a function of the state. Okay, I've never heard of iterative deepening. Richard, you come up with just a lot of terms that are very useful to us and very interesting. I'm not aware of these things. Okay, so I can guess what iterative deepening might mean. As a function of the state, determines the order of visitation of a nodes in a search tree. So things like IDA star, which I don't know what that is, but well, A star, I understand. I don't know what IDA star means. You can find the lowest cost path as kind of a least action, least computation principle. That's interesting. So, okay, so iterative deepening, the concept would be, okay, so that I see, I understand the idea. So, I mean, that's basically a what are you going to, i.e. here, that's a what are you going to compute next? Where are you going to advance the evaluation front next? That makes sense? Christopher.
Well, the most general way to do it is to feed a function that takes a partial evolution object and tells you where to compute next.
Yes, obviously, but the whole point of language design is to come up with a version of this that isn't absolutely incomprehensible, right? I mean,
sure, but
as I've said a million times,
deepening is what it sounds like.
Is what? Yes.
Iterative
deepening. Yes.
Yeah.
I should probably go soon. Christopher, do you have any great ideas for how to specify these things?
Not really.
Do you at least understand the point?
I mean, aren't there like just a massive number of these?
Yes, there are. Yes, there are. And the whole point is that this is, but just like there are a massive number of operations you can do on lists, and you might just say, there are a massive number of operations. There are a massive number of ways to rearrange a list.
Well, but like you sort of need to, let me see. I mean, if you sort of need to be able to refer to expressions that don't exist yet, don't you?
Yeah, I agree. I think that's part of the problem. You need to be able to, but I think you might say the same thing about lists. About list, like.
Well, no, because you do one operation and then you have the stuff, the expressions exist, and then you do things with them.
Fair point. So what we're saying here is,
well, if you have a function like reverse in advance, it doesn't know yet, like when you define reverse function, it doesn't know yet how many elements they're going to have, but you can still do it.
That's true.
But so, I mean, there's special cases of event orders which are easy to define ahead of time.
Such as?
Well, such as you sort by generation first and then by age of a token or something.
Right. Right. By age of a token means you have generation is just a tick of the clock, and you go through and you have some ordering of tokens, right? You have to have an ordering of tokens. You say, let me go through and consume as many tokens as I can, first of the oldest tokens and so on, right?
Yeah. Yeah. Basically, one way to do it is that you have some sorting criteria like generation, age, event number, and so on. I mean, event index or rule index, and other things like this. And then you specify a list of the sorting criteria by priority.
Right. You sort tokens then then consume the first ones or something.
Yeah.
So you generate an ordering on tokens, and then you consume some.
Right. Well, you're generating order on events, not tokens.
Oh, that's
In
right. Yeah.
general.
Right.
Yeah.
Right. Well, but
And
no, but I
consume
mean,
the first one.
tokens, which then lead to, which can be involved in certain events. Because these are events that haven't happened.
In general, you sort events because tokens, like if you want to sort by rule index, for example, it has nothing to do with tokens at all.
I know, but the whole point is on a given branch, if we're not talking about branch-like separated things, the set of all possible events contain many events which are branch-like separated that cannot simultaneously happen.
Sure.
Right? So we could imagine if we're doing a multi-way, thing, we can generate all possible events, including ones which cannot in the same branch of history occur. And then we could do a sort of all of those. But there's a different issue, which is in a single branch of history, I think we're more like sorting tokens.
Well, no, because you can still have things like rule index in a single history.
Yeah.
Not to mention, you can have, well, when you have multiple tokens, sorting sets of those tokens is more complicated than sorting individual tokens. Because, for example, how do you distinguish between, say, 135 and, well, 145 and 235, or 14 and 23?
Mm-hmm. Richard is commenting here about using look ahead. Some parsers need to look ahead some number of symbols. GLR parsers, I don't know what those are. Usually I know about LA, LALR1 and so on parsers. Oh, I see. These make parse forests exploring all possible derivation trees and then using user-provided disambiguation rules. Okay, so that's a good point. That's a good example. That's another example, is parsers are another example where essentially precedence, etc. Precedence gives one gives one a it's not a foliation, gives one an ordering basically on transformations. Right? Which transformation do you do first? That's an interesting case because a parser in general can have lots of ambiguity, which is disambiguated by things like precedence, I believe. Well, we should probably, look, Christopher, your comment, basically what we're looking for is a parameterization of evaluation fronts, AKA,
do you want every one, or do you want
no, I want the ones that
ones
we care about. I want a language for describing evaluation fronts that matter. Just like, in principle, one could do any, you've given a list of size n by m where those aren't specified. You could do any transformation you want on that list. You could, it's like, I suppose permutations would be a good example of a case where you could do anything. But the question is, which permutations do we care about? And maybe with permutations, that's not a great example, although we might think about permutation groups and things like that, where there are permutations we care about, so to speak.
Well, maybe, there is a most general version which could handle everything, which is like you give it a function, and the function just, it looks at all the tokens available at any given moment, and it decides what it's going to, which rule it's going to apply or something like that. So that's like the most general, which probably gets all the foliations. And then after that, I don't know, I just don't know what the useful, certainly depth first, breadth first are useful. I don't know which others really, I don't know any use case for any others.
Well, but that's why things like, the whole point is we're generalizing beyond just getting those are just total orderings. We're saying some of the observers here don't get the objective of breadth first search is ultimately to just get a result, by a certain ordering. So you're using a total ordering and you're going to, as soon as you have a winner, you're done. Whereas here I'm saying there are other forms of output that you might want that involve describing the ongoing computation rather than just the winner, so to speak. I mean, this is still, Well, look, I haven't, right. I think it's probably worthwhile to look a little bit more at these goals. Ah, boy. Carlo, do you have any other thoughts?
It's nearly 1 a.m. for me, so.
Okay, so you've almost reached a normal form for the day.
Yeah, you can say that.
That sounds ominous.
Anyway, all right. Well, look, thanks people on live stream, particularly Richard and Marco, who've had all kinds of interesting things to say. All right. Well, we should probably wrap up for now, and we will continue another time. Thanks much, everybody.